Okay, dear students, today we will see process concepts, process scheduling, and operations on process. Let us begin with process concept. Now, an operating system executes a variety of programs. These variety of programs we can consider as batch system. In the batch system, it operates many of the jobs are executed. In time shared system, user programs or tasks are executed by operating system. Now, in many of the textbooks you will find the term job and process, which are used almost interchangeably. So don't get confused with this. You may use processes or jobs. Both of the terms mean the same thing. Now, a process is a program in execution. This means that a process execution must progress in sequential fashion. Whatever program you have written in whichever language, when you execute it, it is considered as a process. Now, a process includes program counter and registers, stack and heap, text section, data section. Now, when a program is loaded into memory for its execution, this much area is occupied by a process. Now, here we will consider a program as a process because it is in its execution. So there has been some stack utilized, heap, there is data section, text section. Now there are process states. Each and every process undergo many of its states throughout its life cycle. A process executes it changes its state. When a process executes, it changes state. Now these states are new. When a process is being created, this state is new state. When instructions are being executed, then the process switches from new state to running state. The process is waiting for some event to occur, such as an I/O completion or reception of a signal. Then the process switches from running state to waiting state. The process is waiting to be assigned a processor, then it is in its ready state. And when the process has finished its execution, then the process enters its terminated state. So this diagram illustrates all of the states that a process goes throughout its life cycle. See, when a process is created, it is in its new state. When it is admitted to ready queue, indicating that now it can be executed by the processor, then the state has been changed. Now it is ready state. When a processor is allocated to this state process, it enters from ready state to running state. Now, in its execution, when there occurs an interrupt or it waits for an I/O event, then the process switches from running state to waiting state. And when I/O is completed, it is again into ready state from waiting state. Then it switches from, when the processor resumes its execution, then it switches from ready state to running state. And finally, when all of its execution is over, then it terminates. Now there is a concept called as process control block, PCB. Some information is associated with each of the process. Let us see what is this information. A process state. Just now we have seen there are various states through which a processor changes during its execution. Then a program counter is associated with the process. CPU registers are there, CPU scheduling information, memory management information, accounting information, and IO status information. All of these information is associated with each and every process. So all of this information is included in process control block. Now this diagram demonstrates the execution of a process when CPU switches from process to process. When CPU switches from one process to another process, then what are the steps of execution? How the process executes? Let us see. There are two processes here, P0 and P1. The processor begins with the execution of P0 here. The timeline starts here. Now, after some time, there occurs an interrupt or a system call. This indicates operating system to save the state of this process somewhere, because here the CPU will now switch to some other process for its execution. Switching from P0 to some other process and then coming back to P0 again after attending the interrupt, the CPU must know where to begin from. To make it easy for the processor, the operating system saved the states of of P0, that is process 0, into process control block of that process. And now see here, process 1, till then process 1 is idle. Now when it loads from, see, the time P1 was idle, it also has its own PCB. And now here it's time for PCB to execute. Therefore, CPU will read out the information from PCB1 and will start executing P1 will start executing. So this is the timeline which shows the execution of P1. Then here there occurs an interrupt. So its state is saved into PCB1. For that time, P0 goes idle. Now it's time for P0 to resume. Therefore, CPU loads information from PCB0 and starts executing P0. This is how your CPU switches from one process to another process. This is called as context switching. When CPU switches to another process due to some interrupt or system call, then system must save the state of the old process and load the saved state for the new process. The context switch time is an additional overhead here. It requires some more time for CPU to do all these things before switching to another process and start execution. The system does no useful work while switching. See, the system is not doing any useful work while context switching. So it is always preferred that context switch time should be minimized here. This is context switch is time dependent on hardware support. Let us see what is process scheduling. Process scheduling queues are there. Job queue is used to set all processes in the system. That means job queue will hold a set of all of the processes that are in the system. Ready queue will hold set of all of the processes that are residing in memory and is ready waiting for the processor to execute. There is another type of queue which is called as device queue. and it holds set of processes waiting for an IO device. Processes migrate among the various queues. While in its execution processes, they switch from the states throughout their life cycle. They also they migrate from one queue to another queue. Now this figure shows you ready queue and various IO device queues. See here we have queue header. Now queue has got some information here. Like all of the processes we have, for each process we have PCB. So now here in this figure at the top you have PCB 7. It indicates this is P7 process, and then PCB 2 for P2 process. Now at the queue header, this is a ready queue. So it has got two information, the head and the tail. The head indicates which is the process that is to be executed first. So it is obviously P7. So it points to P7. Then there is an internal link maintained to indicate which one is the next process, and so on. And the tail indicates the last process in the ready queue. Similarly, here we have magnetic tape unit 0. So this is a device queue, as magnetic tape is an external device. It also has a head and tail, but there is no process information is there. So none of the processes using magnetic tape 0. Whereas magnetic tape unit 1, we do not have anything. Here disk unit 0 has P3, P14 and P6, and so far we have process control block for each of these processes. So head indicates P3 and tail indicates P6, which is in the last in this queue. So these are the processes which are waiting for disk unit 0, sorry. Now at terminal unit 0 we have process 5. As this is the only process here, so head also points to this and tail also points to the same PCB. I hope you have understood this. Now here we have a representation of process scheduling. How a process is scheduled from one queue to another queue. See, at initially whatever process the processor needs to execute, it will read out a process from the ready queue. From the ready queue, the CPU reads a process being allocated to a CPU. Then CPU start execution of the process. When there is an IO request, the same process is shifted to device queue for a particular input-output operation. When an IO is completed, it again is shifted to ready queue, and the processor again reads it and executes it. Even if there occurs a time slice, see, if it is time shared system, then we have to be very particular about the time slice which is given for that process. So if the time slice expires, then also the process is again shifted to ready queue. If there exists a fork system call. Now this fork system call initiates the execution of the child process holding on the parent process. So then also the process will be shifted to ready queue again. Now when there is an instruction that waits for an interrupt occurs, in that case also it is shifted to ready queue again and then resumes from there. Now there are two types of scheduler, long-term scheduler and short-term scheduler. Long-term scheduler are also called as job scheduler. Now the function of this scheduler is to select which processes should be brought into the ready queue. So now here the long-term scheduler decides on which processes will be brought in to the ready queue. The short-term scheduler, also known as CPU scheduler, it decides which among the processes should be executed next and allocates the CPU. Now we will deal with these in chapter number 5 in detail. But for now, you just consider that there are two schedulers, long-term scheduler and short-term scheduler. So the job of long-term scheduler is to decide which of the processes to be loaded into the ready queue, and short-term scheduler will help in making the decision which process to execute next. The short-term scheduler is invoked very frequently, maybe in milliseconds. So the short-term scheduler must operate very fast. It should not take longer time as it is invoked very frequently. The long-term scheduler is invoked very infrequently. So this can be slow, even in seconds and minutes. Long-term scheduler controls the degree of multi-programming. The processes can be described as either IO bound process. By IO bound process, these are the processes that spend more time doing IO operation rather than some computation, and many short CPU burst cycles are there. Whereas CPU bound processes are those processes that spend more time doing computation, and they have very few long CPU bursts. Now some systems have no long-term scheduler. So in that case, every new process is loaded into memory. The system stability affected by physical limitation and self-adjusting nature of the human user. Now we'll move on to operations on processes. The first operation that can be carried out on a process is its creation. Parent process creates children processes, which in turn creates other processes, forming a tree of processes. Now when a parent process creates children process, we have an option of resource sharing. The parent, now options are parent and children share all of the resources among themselves. Second option is children share a subset of parents' resources. And the third option, parent and children share no resources. Even we have execution options as parent and children execute concurrently. This means parent and children may execute simultaneously, parallelly. Second option is parent waits until some or all of its children have terminated. We again have address space option. The address space can be either shared by the parent process, like if child process is a duplicate of parent process, the same program and data space is shared with the child process. If the child process has a new program loaded into it, so it may have a new space assigned to it. Here we have a Unix example. Fork system call creates a new process. An execute system call is used after a fork to replace the memory of the process with the new process. Now here is a process on a typical Solaris system given in a tree format. This is the program that forking separates the process. Now this diagram shows process creation. After a fork system call is executed, a new process, that is child process, is created. And the child process execute with X system call. Till then the parent wait. The child, when it terminates, then the parent resume its execution. Next operation on process is termination. Process executes last statement and asks the operating system to terminate it via exit. So process termination is done when the last statement of the process is executed, and it then raises a system call for operating system to terminate it via exit system call. This returns the status value from the child when it is received by the parent, and the parent receives the status of the child process. Till then the parent execute wait system call. The process resources are deallocated by operating system. When the execution of a process is over, whatever resources are being held by the process is deallocated, is taken back by the operating system. Now, the parent have a right to terminate the execution of children processes by invoking kill function. Now, when the parent can invoke kill function, here are some of the cases. In case child has exceeded allocated resources, then parent can invoke kill function. If the task assigned to child is no longer required, then also parent can invoke kill function. And lastly, if parent is exiting, if parent itself is terminating, then it can invoke kill function. Some of the operating systems do not allow child to continue if its parent terminates. So when the parent process terminates, obviously the child processes also terminates, and this type of termination is called as cascading termination. Now, inter-process communication we will see in the next session. Till then, take care.